Hello, all developers over there. I am Ricardo from The Construct, and today I'm very happy to be here to talk about how to program robots. And well, today we are going to talk about the very special way of programming robots. You probably are aware of programming robots by creating the very nice algorithm, which is about, I don't know, how to detect the mug, and so the robot can perceive with the camera, and then you create a very cool algorithm that detects the mug in every position, in every situation, light conditions, and so on. But that's the, let's say, the class of programming a robot. And the bad news is that this doesn't work. So that's one of the reasons why we don't have intelligent robots at home. Then the other approach that we are trying, the programmers of robots, the people at artificial intelligence, roboticists, then is about making the robot learn by itself how to discover what is a map in this case, under different light conditions and different situations, maybe occlusions and so on. Okay? So that's the learning approach. So basically, in this case, as developers, as programmers, we are creating the programs that allow the robot to learn what is interesting. Okay, so that's what we are going to talk today about a method, a way of doing a procedimental way of doing this kind of programming. Then this programming, this learning method that we are going to apply, it's called reinforcement learning. Okay, so we are going to learn a little bit more about this, what it is about, and how we can apply into robots in a more or less easy way, okay? So that you can reproduce to different robots of different types for different learning tasks, etc. So that's what we are going to talk here today. And here you have the chat and the questions and answers that you know. So I will keep doing it. Moving with the presentation, but you can be putting your questions there, and then at the end I will have a look and answer as many as I can. Everybody ready? Yes. Yes. Okay. Those online conferences, they are so cold because you cannot feel the feedback of the people, and not usually people is hidden behind the computer over there. So I don't know if you are 100 over there or you are only a couple of people, or even nobody, because I don't see anybody on the chat. Let's have a look at the chat. So say hello at least. So tell me hi. Are you there? Can you see the presentation? Can you hear it? Okay, yeah, we have one. And unfortunately, I cannot pronounce your name. It looks to me like it's a Russian name, and it's one of the speakers. Oh, thank you very much. My honor that you are attending as another speaker. So it is my honor that you are here. And okay, so one person so far is there. Well, let me start with the conversation. Oh, another one, Victor Pau. Hello, Victor. Nice to have you here. Pavel. Okay, Pavel. So that's your name, Pavel. Thank you very much for helping me on this, Pavel. Then Pavel, Victor, Remo. Very well. Very nice. Very nice. So, okay. Pouron. I don't know if I have pronounced correctly. And then I usually do live classes online, and every Tuesday, and on YouTube, and it's like this, it's live. And then so I'm used to do this kind of things, and we always start presenting and do the presentations and talking to the people, because it makes this more approachable. So it's not, I don't like this kind of approach very, very fun. So nice to talk to you all there. You know, the chat is there, the questions also. Let's start with the presentation. And it contains a little bit of practice. And at the end of the presentation, I'm going to share all the code, all the documentation that I am presenting here with extra instructions for yourself, so you can go even further. And all this, of course, is for free, and you will get this. So you can continue if this subject is interesting for you and you want to actually do it and apply to any other robots that you may have. Okay, so as I mentioned, it's about programming robots with a technique which is called reinforcement learning. Okay, reinforcement learning is one learning technique. It means we create a program that allows robots to learn by themselves how to do a task, how to solve something that we want the robot to do. Like, for example, I mentioned about discovering how the map, where is the map, or if there is a map in the scene. Or it could be to bring us the Coke or the beer from the fridge. So it depends, that's the task. Okay, so then in any reinforcement learning task, in any problem, let me show you here in bigger and remove some stuff here. Yeah, so in any reinforcement learning task, you have to define the following things. First, you have to define which is the environment. The environment is so as the word that it says, is the environment in which this robot is going to operate. Robot or a system. So reinforcement learning is not only applied to robots, but it can be applied to learning anything that needs to be learned. Like it could be also, for example, to recognize characters or recognize a voice or learn how to play a game. All those things. Actually, the application of reinforcement learning into robots has been only recently in the last years, because it was very difficult to apply, and reinforcement learning was applied to many other subjects that are not robotics. So the problem of reinforcement learning. So when you want to do a reinforcement learning learning, so you have to first define the environment in which the agent, the robot in this case, is going to be working. Then you have to define the task that has to be solved. So in this room, I want the robot to be able to grasp the map. So maybe that's the one example, the task. That's the task. Then you have to define the sensors that the robot has in order to accomplish that task. So the robot is going to be working on cameras, for example, for detecting the objects, or is going to be working on point clouds. Point clouds is like a typical Kinect device that you already know. So maybe that's it. Or infrared. So because my coffee is hot, the robot can use this temperature to detect this. I don't know. So it depends. Okay, so you have to define the sensors, but also you have to define the actions that the robot can do. The actions are all the things that the robot can do on that environment. For example, it can rotate the head, it can move the arm, it can open and close the gripper. Those are the actions, but not how to use them. Okay, so in this environment, in this reinforcement learning setup, what we want is the robot to learn how to use all this to solve the task of bringing me the coffee, for example. So that we don't program how to use the arm to extend, to put it closer to the body, how to open the gripper, how to look at it. We are not saying that. We just say to the reinforcement learning algorithm that this is available. And then, based on the task, we define what is called a reward function. And the reward function is a function that we, the programmers, the developers, we are defining based on what we want the robot to achieve. For example, I will give 1 point if the robot brings me the coffee, or 0 if it doesn't. For example, that could be something. Then here I have a comment from Victor that says, can you zoom the document a bit? The screen is hard to read. Okay, yes. So this is, okay, great. I hope that this is better. Then, so that's the reward function. And basically it's about how to indicate to the agent if it's doing okay or not. Then the whole reinforcement learning training, it's about using all this stuff in order to learn what is called the policy. The policy is like you can imagine like a table that says what the robot has to do on every situation that it encounters. Okay, so that's a broad way of explaining. Okay, so, and then here on the picture, you have the image. The agent, we call an agent, is the intelligent program or the entity that we want to do something intelligent. It could be the robot, for example. So how it works, the whole reinforcement learning training works is as following. So we have the agent with his sensors and actuators. Then the robot looks at his current policy, which may be all zeros because he's starting right now to learn. And then based on that, he decides to take an action of the ones that are available, maybe extend the arm. So he produces this action, and then we see this action is implemented in the environment. So we see what is the result. This action implemented in the environment, we see the result, and then from the result, we get two things. One is the new state. The state means basically the perception. So the sensors of the robot, they are going to identify what is the situation. For example, I extend the arm and then I crash against this. Okay, so that's detected by the sensors, by the cameras, by the contact sensors, whatever it is. So we are providing this information to the reinforcement learning algorithm. And also we provide a reward. This reward that is computing if I am doing it correctly or not. For example, if my reward function says, oh, if you get closer and closer with the gripper to the mud, then the closer you get, the more reward you are going to get. Okay, so that's an example. And then if you crash against something, then you have a minus 20 reward. If you get close, then it depends on the distance, this score, this reward. Okay, so we compute those two things from the actions, from result of the actions, and then we use this in order to update this policy, this table of things that the robot is learning. And the way that this is done, it depends on the algorithm of the reinforcement learning that we are using. So there are different reinforcement learning algorithms. But basically the loop is this one. Okay, then, so what happens now? So I haven't explained now what is the reinforcement learning training system in order to make a robot learn something. The problem is this algorithm that I mentioned to you, that is the one that is updating the policies. So how do we update the policies in order to learn optimally and learn the things that we really want to learn, not other things that can confuse the robot? Then in this case is when OpenAI comes into the picture. OpenAI is a company that is based in San Francisco in the United States, and they are doing amazing things on artificial intelligence. But one of the things that they have done is to create a set of reinforcement learning algorithms implemented in Python 3. So anybody can use them already implemented, because if you study reinforcement learning, then you will see, oh yeah, the algorithm does like this and does like that on the book. But then afterwards you have to translate into code. So everybody's translating this into code the best way that they can. But most of the times, the people that are doing this, they are not developers like you. They are just engineers like me, or robotics, or mathematicians, and then their skills in programming is not so good. So then OpenAI decided, okay, let's take some of the most important reinforcement learning algorithms and let's implement ourselves, that we are experts on this, and provide it to the public. So then that's what they did. And you can get the OpenAI algorithms. Let me see where I put it. Remember that I'm going to share this with you by the end, so don't worry, you will get all the information here. So yes, it's called the OpenAI baselines. The set of algorithms that OpenAI has created for reinforcement learning algorithms in Python 3. It's called the OpenAI baselines. And they have implemented all of those here that you can see. If you go to the repo, you will see the implementations and also instructions about how to download them and use them. They did a very interesting breakthrough in artificial intelligence when they applied their system into the Atari games. You know, those games, the old games of the consoles of the past. And so they apply those reinforcement learning algorithms and make the system, the computer, to learn to play those games and win at those games without telling them about anything about the rules. The only thing that they provide to the algorithms to learn was the environment, that is the pixels. Not the pixels, this area, the area that they have there. Then the actions that the robot can do, not robot, but the character of the game that can move to one side to another, for example, or can fire. It depends on the game. And when a score that's saying, oh, you are winning or you are not, based on the scores of the game. Then by just launching this, the robot learned to play the games and win without knowing any of the rules previously. So that's very impressive. That was a very, very impressive result in artificial intelligence community. And now you can do it because actually together with the baselines, they have created what is called the OpenAI Gym. The OpenAI Gym is a way for you to reproduce those results and even to create your own. So you can make your own game or apply this to your own game by using the OpenAI Gym. But today we are concentrated on the baselines, okay? So on the baselines here, which are the implementations of the different reinforcement learning algorithms. Okay, so this is how it applies to a program, because at the end, the Atari games, they are just programs. Then how can we apply to a robot? Well, with the robot, it's exactly the same. As I mentioned to you before, you have the same loop. So this is a robot, which is called Sawyer, if you know it. And the loop is exactly the same. You have the reinforcement learning algorithm here, the robot in the environment, it's here. So the reinforcement learning algorithm decides an action that the robot is going to perform in order to solve the task. And then it sends this action, the robot executes it on the environment, and then we obtain the observations as well as the reward. So it's basically the same, but applied to a robot. The thing is that for robots, it's not as simple as Atari games. So the Atari games and other reinforcement learning problems, they are a lot simpler than robotics, because robotics has a lot of other associated problems. Especially that the space of actions and observations is super huge compared to those Atari games and other reinforcement learning problems. But anyway, we are working towards this, and then we are doing experiments with this. So in order to do this training, this loop, as you may understand, you need to execute this loop many, many, many times, because only by taking one action and seeing the result, okay, the robot can learn just a little. And then we need this to be repeated all the time, as fast as possible. So as fast as possible, because then that would mean that the robot is able to learn as much as possible and faster. Okay, then in that case, what we do in general, 99.9% of the cases, is to use a simulation. We don't use a real robot to do this training because of several reasons. Some of the main important are that the robot, so by doing this, you don't have to deal with the hardware. You don't need to have a hardware robot here. And in your case that you are developers, I think that this is especially appreciated, because if you are the software programmers, then that means that in most of the cases that you don't want to use the hardware. That's why you are developing software, because you like it more. And in this case, for you, that's very convenient, because you only have to deal with software simulations of the robot. That doesn't break. You don't have to set them manually back. So imagine training a robot with reinforcement learning. So every time that the robot does something wrong, for example, here trying to grasp the mug instead of the bottle, but it does like this, it fails, and then okay. So then for the next training cycle, somebody has to come and put it back, the environment, because this is the environment in which you want your robot to be working, for example. So in simulation, you don't need to have that. You only, because the own simulator, you can program it to reset to the initial condition. You are going to see this working in a few minutes when we do the demonstration with the carpool. Also, having simulations, you can make them train faster, because in reality, the robot can move only at a certain speed. But in simulation, you can put a bigger computer and then make the simulation. Hey, wait. Don't. Yes. Okay. So in the simulation, you can make the computer to run faster. So you can make the more trials in less time. And also you can even parallelize. So you can make the robot learn one part in this computer, another part in this other, and then put many simulations in parallel. So you can speed the training a lot. And then, okay, so training on simulations is not all benefits. You also have some drawbacks, and is that the simulation is never going to be the same as the reality. So there is one thing that is called the reality gap, which is the difference between the simulation and the reality that you are trying to simulate. And then depending on how big is this reality gap, how far is your simulator from the reality that you want to learn, then what you learn during the reinforcement learning training in the simulation will apply more or less into the real robot. Okay. In order to solve this problem, also there are some other techniques that they are starting to appear, like domain randomization, which allows to train with noise, and then the robot can learn into modified situations of the current simulation. So when you apply into reality, even if it's a little bit different from the simulation, then the code is ready for it. So it's more ready. And basically that's one of the problems. That's the problem by training on simulations. And there are some people, for example, at Google, they have created a very huge space in which they have put many tens of robots, all training at the same time, grasping things from a bucket. And yeah, so they try this, and yeah, so that you can do this with one specific robot for one task. But what about training other robots? You cannot do this with many robots, the same robot and different tasks. So that's not scalable at all. And then simulations is going to be the future for robotics, because that's what allows to train in many different conditions, simulated in parallel and faster. Okay, then we have this reinforcement learning. We are going to use the simulation to train the robot to make the actions and get the feedback and so on. But then we need to put all those three things together. First, the training algorithm. Well, three things, yeah. The training algorithm, the robot, and the robot simulator. Okay, so two things. And for that, we need three components. First is to have a common framework for programming robots. So we can apply this method to any robot. So some years ago, that was not possible. So if you created a reinforcement learning training algorithm for an arm robot of brand A, and then you want to apply to brand B, and it doesn't work. You have to modify again all your code in order to apply to the second robot. And that's not optimal at all, but it's not, I mean, it's making advanced robotics very, very, very slow because we were reinventing the wheel all the time. So what we are going to do is to use a common framework for programming robots. Then we need also the robot simulator. And then finally, we need an interface from those two things into the OpenAI baselines. Remember, we are using these OpenAI baselines because we know that they are very good implementations of the algorithms. That's the reason, because OpenAI very professional, very good results, and then we trust them. So we don't have to be reinventing again also those algorithms. So let's go step by step. So the first thing I want to talk here of this schema is the common framework for programming any robot. And the one that we are going to use is called ROS, Robot Operating System. And what is ROS? What is the advantage of ROS? Well, actually, ROS is not an operating system. It's called like this, but don't pay attention to that. ROS is a framework to program robots. And the main advantage of this framework is that it is abstracting from the programmer all the hardware. That means that at the end, when you are creating a ROS program for a robot, you don't have to care very much, very, very, very little. You will care very little about what is connected in the robot. What are the sensors? What are the actuators? And that's the problem that we had in robotics before ROS, is that every sensor and every actuator, every device that was connected into the robot, then it was from a different manufacturer most of the times, and then you need to integrate this inside the robot, and it was very difficult. Also, if you needed to change one type of sensor, let's say a LiDAR, by another LiDAR from another company, that was a nightmare. So we needed to have a common ground. It's like the Windows for a PC or the Android for the different mobile phones that we have. You know, the Huawei, the Google phones, and all those brands, they have the Android and they can work, even if the hardware is different in the inside. So ROS is doing this for robots. So you have different robots from different brands with different sensors, and they can execute the same program, actually. Let me explain you graphically. So you have a ROS robotics program in a robot that has this laser, and then you want to change this laser because it's broken, because you want to put more it's a better laser, and then you replace that one by another one from a different brand. Then in case that you are using ROS, then your program actually doesn't care about this. So it will not even notice that it has been changed, because ROS provides a ROS API to any device that is connected to the robot. So if this laser is connected to the robot, then it's going to have the same ROS API than the previous laser, because basically they are doing the same function. Okay, is a laser for detecting obstacles. Then you are changing one brand by another, but not the functionality, right? Then, because of functionality, we don't care as programmers of what is the actual sensor over there. So that's what ROS is doing. It's abstracting the hardware for the programmer. So he doesn't care what is actually attached as a sensor. And also what this implies is that you can create a program for a robot of brand A, and then use the same robotics program into a different robot of brand B, provided that it has the same structure. I mean, it's for the same functionality. In this case, it's an armed robot to another armed robot with more or less similar sizes, because they are going to work on the same environment. But you don't care about the brand, actually. That's a huge, huge improvement of what we had before. Okay, so in case that you are interested on learning about this, tomorrow I will deliver a workshop. It's 5-6 hours long, where we are going to learn in deep. So you are going to be learning, practicing with me about programming ROS and so on. It's tomorrow, in one of the workshops, and then have a look. It's about how to program robots with ROS. You are welcome to attend. Okay? And that's, yeah. Then, so we have this framework for programming the robots, and then we have the simulations for robots. In simulation for robots, we have Gazebo as a simulator that is going to provide the simulation of the whole environment. And the Gazebo is very well integrated with ROS. And what that means is that you can create programs that work on the simulation, and you transfer this to the robot, and you don't have to change any code, because they both, the simulation of the robot and the real robot, they have the same API. So, as I explained before, for the program, it doesn't care even if it is connected as simulator to itself. So the ROS program, it just sees the ROS API. And then what the information from where it comes, the information for that ROS API, it doesn't care, the ROS program. So the Gazebo simulator, you can see here some examples of environments simulated with that. It's not very, very, very close to reality, but it works. It works enough for this situation. Has some limitations. I'm not going to talk about this, but we are using this in many, many cases. Wanted to show you this other one, which is one based on Unreal Engine, and which is for autonomous cars. Then it starts to become more necessary to have more realistic simulations. So in this case, is an Unreal Engine based simulator called Carla for autonomous cars. And then in this case, we can get more precise information, more close to reality. And we need this in order to train the autonomous vehicles. But for this is something more complex. It requires a lot more work to be done by you. But for Gazebo, it's out of the box. You get the Gazebo simulator when you install ROS. So it's very easy. Okay. Then, yeah. So then we go, and then the final part is how do we integrate those simulations, those ROS environment, and the OpenAI baseline reinforcement learning algorithms. And that's when the OpenAI ROS package comes into the place. It's the one that creates this glue between all the parts. So by using this OpenAI ROS packages, what we can do is the following. We can train any robot on any task using the baselines, and we can change any of those components without changing the others. That means that you can train, for example, let's say this robot here that we have here on the side, the robot on grasping a mat, but then use different algorithms in a kind of way of plug and play. So you can try different algorithms, even your own algorithms, but you can try the different ones of the baselines, for example. Also, you can keep the same algorithm and then change the robot. So you can put different robots to be learning the same task with the same learning algorithm. Or you can do the other way around. Then you can train the same robot with the same algorithm on a different task. So now to learn how to grasp the max, but then is how to wash clean the room, for example. Okay, so that's the structure that is provided by the OpenAI ROS packages, but with the help of the Gazebo simulator, the ROS framework, and the OpenAI baselines, putting all this together. Okay, so basically an OpenAI ROS package is divided into two parts. Let me go, well, you can see here many parts, but we are going to call one part the red one and the other one all the rest here. So let's go for the first part, which is the training script. Then, yeah, let me have some coffee. Great. Then the training script. So the training script is the one that is going to define which one is the algorithm that you are going to use. And for example, the baseline that you would like to use. And then the way that is structured in this case, it is composed of two things. The first one is the baseline algorithm, which is the one provided by OpenAI, that you can put it there. And then the second one is a config parameter file that it's providing the configuration parameters for the learning algorithm. So every learning algorithm requires to be configured with a set of parameters. And then the learning algorithm efficiency depends on which parameters you are going to use. So in this area, we are separating the algorithm that is provided by OpenAI, and then a file, an external file that contains a parameter. And this is going to allow us to change this file, actually have several files of different config parameters. So when we train the whole thing, we can test which parameters are the best for us. So we can and then the only thing that we will have to do in those cases is to modify the parameters file. So that's why we have separated this part here as the training script in those two parts. And also here is the place where you can plug and then unplug different baselines. So you can use another algorithm and maintain all the rest, all the communication with the robot, all the task, define and reward, all the action observations, everything, all that is maintained, and then you can plug and unplug different baselines provided by OpenAI or your own algorithm even. You can put it there, plug it, and maintain all the rest, and then see the results without modifying all the whole pipe of training. That is very, I'm putting some stress in this because it's a little bit complex, this thing, because you need to have all these pipe of launching, having the simulation, then taking an action from the policy and sending that into the simulation. Then the robot does something, you have to manage the control of that simulation, when to stop, when to reset, and all that. And then produce the observation and the reward, and provide this information into the learning algorithm. So that's a lot complex in a robotics situation. And that's why we need this structure. Maybe it looks a little bit complex, but it's a way of simplifying this problem so we can do experiments in a very fast basis, in a very changing different basis. So that's a training script. And then what the rest of the parts, what we call is the training environment. With the training environment, what we have is 3 different classes. Everything here is implemented in Python 3. And then for the 3 different classes, what we have is one class, which is called the Gazebo Environment. And this is the class that is in charge to connect to the simulator. This is provided by the package OpenAI ROS, and allows you to connect your reinforcement learning task into the simulation. Any simulation is the same Gazebo environment. Then we have another class, which is the robot environment. And this is the one that is specific for the robot that you have in the simulation. And it's the one that is in charge of sending the actions to the robot and getting the observations. Then finally, you have the task environment, which is the other class. And this is the one that defines what we want the robot to solve. So it's the one that gets the action decided by the baseline and sends it to the robot environment and says, hey, please execute this. And then gets the result of the observations and computes the reward. And then says this reward to the policy, to the baseline algorithm, and say, hey, your last action that you provide me, the result is this. So this task environment depends on what we want the robot to execute, to accomplish, and the robot environment depends on which robot we want to use on the reinforcement learning. The Gazebo environment depends on which simulator, but so far it's only available for Gazebo. So we provide several robot environments already done on the OpenAI ROS package for all those robots here, the Carpal, the Sawyer, Shadow Robot, Startlebot. I don't know if you know this, they are quite famous in the robotics community, service robotics community. So they are already done. So you don't have to implement those robot environment for those robots. They are already done. And for task environments, we also provide some examples, but usually the task environment, it depends on you, what you want the robot to look. So that's basically the structure. It's a lot more complex to understand, but for you as developers, software developers, it's going to be very easy to understand, I think. Then we don't have the time to explain it, but you have more material about this, about how to learn about this below on this document. So now I'm going to give you an example with the Carpal. So what I'm going to do is to get back into this structure. Okay, let me see here. Yeah, so the Carpal problem, let me define the Carpal problem. So we need an environment, which is this environment that you can see here. It's the space without anything. And then we have this rail here on which the robot can move along. Then we have a robot. The robot is this one here. And it's a very simple robot. This robot can only move a little bit to the left, a little bit to the right. That's the only actions that it can perform. Then it can only sense the pole angle. So now you can see this pole that is on top of the robot. And this pole is like a pole that you will have in your hand like this. It has no control. So if you move the robot a little bit, then it will fall completely. And actually, if you don't even move, due to the noise of the environment, it's going to fall to some place. So the robot has to learn, the task that it has to learn is how to balance the pole by moving forward and backwards. Probably you have done this in the, I have actually a pole here, and we can use this. So with this pole, it's basically this task of learning how to maintain the pole on top, right? So it's the same task for the robot, but in this environment, it can only move one side to the other. Then the reward function is the more time that you get the pole vertical, then you get points. When the pole gets under a certain angle, 45 degrees, then we consider that you have failed, and then we restart again to train. We start again to train. Okay? So that's the reinforcement learning problem. And we have implemented this using all the structure that I have mentioned. That's a Gazebo simulation. The controllers are ROS-based. And the whole thing is using the baselines provided by OpenAI and the OpenAI ROS package to control everything. I have launched here the simulation, and you have the instructions about how to launch it, and everything is going to run in any computer. So I have already launched this in order to move faster. We have the simulation, and now what I'm going to do is to launch the code that trains using the structure that I have already explained to you. So let me open another terminal here and launch this command. Sorry, I copied the wrong thing. What? Okay, let me select again. Okay, so somehow I'm not copying. Let me see. It's because I have a Mac here. I think I'm doing correctly. Yeah, okay, so I don't know why I was doing wrong. Okay, so now I'm launching the whole training process, and then you're going to see when it starts that the robot is starting to move to one side to the other, and at some point, it's going to go back originally to the original point. That means that the pole has fall down. Yeah, you can see that it starts again on the middle with the pole up. And yeah, you can see how it is trying to learn. So it's launching actions then seeing the result on the robot, and then finally getting a reward and an observation, and using this to update the policy of the learning algorithm. Then, so that now is starting to learn a little bit, and if we leave it like this, then you will see that at the end it is able to maintain the poll. It's going to take some minutes to do it, so we can leave it like this. And here, what I want to just to share with you is that you have here many instructions, step by step, how to use different algorithms, how to change them. So all those instructions are here in the rest of the notebook that I cannot explain because it's a lot of time. And also about the parameters, how to use them, the algorithms themselves, you can see here, and how to change from one specific task or another. So you can follow this and do a lot of other experiments with this and obtain better results than what we have obtained. And check it out. I'm going to share with you this project in the chat, and I think that is all. So we can finish the session here and start with the questions. So if you have any question, put it on the chat or Q&A tab. And in the meantime, I'm going to share this project with you. It's very simple. In order to share, I'm going to go to my home. And I'm going to share this project, which is the one that I have created for the conference here, by clicking on this icon and getting this link, copying this link on the chat. Here, the whole project of the conference. And if you click this, you will be able to launch this project in the same way as I have launched it in your own computer, and you don't need to install anything on your computer. You don't need to have a special computer. You just need a browser. Use Chrome or Firefox. Create a free account there for getting this, and then you will get the whole information, documentation, code, simulation, instructions, and all that. Okay, so that's all from my side. Let me know if you have any questions. There is a question from Victor that says, can this process be applied to simpler robots? Thinking of embedded robots with limited RAM. ROS seems to be only for rather big robots as far as I can use. Yes, that is right. That is right. But there is a project which is called Micro ROS, which applies to small robots, microprocessor-based robots. Then you can use that project. It's still at early stage, but you can do many things. And then you can use this whole approach, because at the end, what you want to have is a set of ROS APIs, and then Micro ROS allows you to provide this ROS API on small robots based on microcontrollers. Mark has answered. Mark has answered. Okay, myself. Okay, so well, I hope that this answered your question. So I Mark has answered. Any other questions? Okay, this chat is a little bit strange. Too many options. Any other questions? No questions? Okay, Victor. Okay, my pleasure. We can see the reward of this robot, how it is evolving, and actually you can even plot it. There is what is called a topic, a ROS topic. This is some instructions based on ROS. And you will learn this tomorrow if you decide to attend. And there is a topic which is called OpenAI reward, and we are publishing there the current reward for each episode. So it's getting 8, 9, 5, 9. Sometimes it goes back on his reward because it's trying new things in order to improve. But at the end, what happens is that you get the best of all of them. You see, in this case, it has stayed for a long time, then the reward was 16, and then in other cases it has less because it's trying new things. Let me see. No more questions? Okay, so I think, I don't know how much time do we have for questions, or, well, if you don't have questions, what else can I show you? Nothing? Okay, then guys, remember tomorrow we have this workshop, which is several hours long length, and we are going to be learning to program ROS. And it's not going to be like this as a talk. You are going to be doing all the time with me from minute one. So come prepare. It's going to be a lot of fun. And yeah, so I have here a message of 7 seconds. See you tomorrow if you want to learn how to program robots. Bye bye, guys. My pleasure.